x is not equal to 0, because if x is equal to 0, then we'll be dividing by 0 here. Now, this is a special formula which you should know, and in general we have that the integral, in general, we have the integral of 1 over x as equal to ln of x plus c. Why? Why do we have this formula? Because it comes from the differentiation. Remember that when we did the derivative with respect to x of ln x, okay, was equal to 1 over x, and we said x should not equal to 0 here, because if it's equal to 0, then we'll be dividing by 0. So because that means that this is the antiderivative of this one. That's why if I take the integral of this, which is this one here, I should get ln of x. Or if I differentiate this, I should get ln of x. So this is the antiderivative of this, and this is also an antiderivative of this one. That's how maybe this can give you the idea of antiderivatives. So they usually they are the reverse of each other. Now you ask yourself, what did I differentiate when you're given to this one? What did I differentiate to get this expression? Okay, then you say ln of x. You can put we put absolute value so that we take the ln of positive numbers. That's why absolute value lines are always there. But usually, I don't think you'll get it wrong if you say x. Okay, I don't think it's wrong, but usually we use this one here. We are going to have a formula which would lead you to another type of a function or integral, where you have the integral of a function over a function with dx. Now this one here, you have a function over a function, and you notice that the top, a function, is the derivative of the bottom. This is given as the ln of the bottom function plus c. But this formula holds only when the top is the derivative of the bottom. Now some of you go on and extend your formula and say f of x over f prime of x dx is equal to the ln of f of x prime. No, this is not true. This is not true. So this formula holds only when the derivative is on top and the function is at the bottom, not the other way around. So this one is not true. So this is true. So actually in words, you say that when you have a function on top over the function at the bottom, and the top is the derivative of the bottom, then the integral of this expression, the whole expression, is just the ln of the bottom function. That's what I'm writing here in words. In words here, I'm saying that if you're given the integral of expression like this, a function of a function, and you with respect to x, and you realize that the top function is the derivative of the bottom function, then the integral, the outcome here, is just ln, ln, not in, ln of the bottom function plus a constant. So I'm giving this in words so that if you have an to integrate a function divided by another function, and you see that the numerator is the derivative of the denominator, then the outcome integral is just the natural logarithmic of the denominator function plus a constant. So this is how you handle this expression. Or you can also use the substitution, but then of course it's a nightmare with substitution. You can always see as you do more examples. Now here, the example to follow this formula here is this one here. You have the integral of sec squared x over tan. Now, with all the derivatives we know, you see that actually the derivative of tan is sec squared. And now we have sec as f prime over f of x. Now f of x is tan and f prime is sec squared. Now f prime is on top, tan is fx. So I have f prime over f of x. Now here, my integral, the outcome of this, is just the ln of the bottom function plus a constant. Also, the next function here is you have the integral of 2x over x squared plus 1 dx. Now, notice that the derivative of the bottom is 2x, and I have 2x on top. Now, what is the outcome? What is the answer? What is the integrand here? The integrand is the ln of the bottom plus a constant. Why? Because the derivative of the bottom, which is x squared plus 1, is 2x, and it's on top. Then I have to use that formula, ln of the bottom. Now, if I had another expression like this, let me expand on this. If I had expression, the same expression, and they ask you to integrate x over x squared plus 1 dx. Now, here, I can use substitution, or I can also use the ln function, but I'm remaining, when I see the expression here, here I'm missing a constant 2. Because when I ask myself, what's the derivative of the bottom? The derivative of the bottom is x squared 2x, okay? But I have x here. I'm missing only 2. I'm going to rewrite this expression on top by introducing 2 there. So x over x squared plus 1. Rationalize the numerator. That's what I'm doing by 2. I want to create 2 with the dx. I'm not changing anything. 2 over 2 is like 1. But I want to introduce 2 on top. Then in that case, I'll put the half at the bottom. Then I'm going to have 1 over 2. This 2 here goes at the bottom here. Integral, the top 2 goes with this x. I have 2x over x squared plus 1 dx. Now, I have this one in the form of, this one now I have it in the form of a half integral of f prime over f of x dx. So I'm just going to say the ln, a half the ln of the bottom. And my bottom is here, so I'm going to say the integral of this one is just ln of the bottom plus c, because I have already rewritten, I have introduced 2 on top. So now when I check, the derivative of the bottom is 2x, and I have 2x there. How did I get 2x? By rationalizing my numerator, by creating a constant which I'm missing. That's how you handle this kind of questions. What I'm doing here, that if you have a function, you have 2 functions, and you're combining them with the constant and with the sum or the difference and so on. So you just have, which I was doing before, now I'm giving it in the formula form. So here in general, a combined function of basic integration formulas, if you have 2 functions like f and g, and they have been combined with the constants and constants a and b, with the sum or the difference, whatever. So what you do, you just separate, you remove the function, the constant a, and leave the function here, and separate the 2 function f of x from g of x, and also in g, remove the constant from g, and integrate g with respect to x alone. So it is just a combination of basic formulas which we know with integration. Now, this is the topic I want to do today, where there is a nightmare of substitution. The substitution integration, either of indefinite integrals or definite integrals, it doesn't matter. So now here let us do indefinite integrals first. What is the substitution method? I think there's a bit of a nightmare of substitution method. Now substitution, you are going to have example as x cubed plus 5 all to the power 100 times 3x squared with x. Now, when you see this expression, remember the examples we have been dealing with, we just have one function, okay, base to the power, or a function of a function, and the top is the derivative of the bottom. Now here I'm faced with an expression with a power and times another function. Now this is where substitution comes in. How does substitution comes in? It comes in when you have a composition of functions. Remember, you have f dot g, which is the same thing that f g of x is inside f. Now here my g is this one here, and my f is x to the power 100. So I have f of x here is equal to x to the power 100, and I have g of x is equal to x cubed plus 5. Now here g is inside f, so that means it's f dot g. If I have a composite function, then I'm going to think of substitution method. And substitution comes in when you have, first of all, you think of a substitution method when you have a function inside another function. Like in this case here, I have a function x cubed plus 5, and it's raised to the power 100. So that's another function. So this is how I'm explaining this one. And remember, I also have another function multiplied through, it's a product of this function. Now you ask yourself, how am I going to substitute my expression here? That means that how am I going to pick my u? Now here I pick my u, I'm going to say let u, I cannot say let u equal to this one because it will not help me. I'm going to say let u equal to x cubed plus 5. Why do I let u equal to x cubed plus 5 and not 3x squared? Because I'm going to differentiate u with respect to x, and if I differentiate u, remember I have u in terms of x cubed here. If I differentiate u, I might end up with x squared. Maybe that x squared might cancel with this x squared here. That's the idea of substitution. Now, I'm going to take the derivative of u here, du with respect to x, dx, is equal to the derivative, power rule, is going to be 3x squared plus 0 dx dx. Now, make dx the subject of the formula. The dx, the subject of the formula here, is going to be cross multiply. Then I'm going to have du over 3x squared. I'm going now to substitute my new variable. Instead of x, I'm going to use u. Instead of dx, I'm going to use du. So I'm going back to my original expression here. My original expression was integral of x cubed plus 5 to the power 100 times 3x squared times dx. I'm going to replace this one with my u variable now u. I said u equal to x cubed plus 5, which is u here. And my u here is raised to the power 100. The 100 stays there. Times this variable, which it stays there. There's nothing I can do. Now from a substitution there, my dx was equal to du over 3x squared. Now you see that 3x squared cancels with this one. Then I'm going to remain with the integral of u to the power 100 du. Now I go back to my power rule. The integral of the power rule is going to be u power, increase the power by 1, divided by that sum, plus c. Now, which I get as u the power 101 over 101 plus c. I can leave it like this, or I can go back and replace my u with my original variable x. I remember I said my u is equal to x cubed plus 5. So I'm going to replace that one as x cubed plus 5. And the u is raised to the power 101 all over 101 plus c. This is substitution method. And you don't make it difficult. You can see how simple it is. You check how am I given. What is the expression? I have expression in this form. The inside here, if I take the derivative of the inside, I might end up cancelling with this one. Then let the inside be my u. Then take the derivative of u with respect to x, make the x the subject of the formula, go back and substitute in your original expression. And now your variable changes from x to u. Then I'm going to integrate with respect to u, and my expression is in terms of u. Apply my integration, and then go back and substitute your u by original variable x. Another example, the same way, you have integral of t e the power minus t squared over 2 dt. The same thing. I have an expression t times e to the power minus t squared over 2. Now also ask yourself, it's not going to help me if I say u is equal to t. Now you ask yourself, what's going to be my u? Now my solution here is going to be let u equal to what? I cannot say u equal to t, because if I take u equal to t, it will not help me with this one here. And I can also say maybe t is equal to this one, but it's going to be so complicated. Let me say now, let my u equal to the power of e, because I know how to integrate e function. So let my u equal to the power of e, which is minus 2 over 2, minus t squared over 2. That's my u. Now if I take the derivative of u with respect to t, now my t, I have to use t now, not x anymore. So I'm going to say du dt. I'm taking the derivative of u with respect to t. This one is going to be minus a half times 2 power rule t to the power 1. So which gives me minus, this 2 cancels with this one, I end up with minus t. Now, I'm going back to make t, dt, the subject of the formula. My dt now, my dt is equal to minus du over t. That's what my dt will be. Now, this integral, remember, it is definite integral. I have 5 here, 0 to 15. I had left it out there. This is definite integral. I have the limits. Now, since I have the limits, these limit values 0 and 15 are the limit values of the variable t. But now, I have changed from t to u. Then also, I'm going to change my limit values from 0 and 15 using this substitution here. U is what I'm going to use. What am I going to say? I said that since I have changed from t to u, then also I'm going to change my limit values of t to the limit values of u. Then I'm going to say that since I know that u, if u equals to minus t squared over 2, now let u equals to that one, we know. Now if t is equal to 0, using this substitution here, this equation here, if t is equal to 0, then what is u? My u is equal to minus 0 squared over 2, which will equal to 0. Now, if t is equal to 15, because these are the limits we had from the beginning, if t is equal to 0, put t equal to 0 in this substitution we had, then I end up u is equal to 0. If t is equal to 15, then what is u? U is equal to minus t, which is 15, squared over 2. So if I simplify this one, it's going to be minus 1, I think, 2, 5 over 2. Now this is my limit values now with respect to u. Now I go back and write my integral. Now in the integral now from 0 to 15 of t e the power minus t squared over 2 dt is now written as the integral. I'm changing the limits here now of, if I said if t is 0, this one is 0. If t is 15, I end up having, this one is minus 225 over 2. Now my t stays there, my e stays there, my minus t squared over 2 became my u, so it's going to be minus u. dt was what? dt was minus du over t. Now this t is going to cancel with this one. Now my new integral, is it? Hold on. No. It's plus u here, sorry. Because I said u equal to minus t. I said u is equal to minus t squared over 2. So my u is plus u here. Okay? My u is plus there. And now my integral is going to be minus integral of e the power u du. And I'm 0 to minus 22.5 over 2. Now, remember, was this minus? Yes. Now remember that my lower bound must be less than the upper bound. Now when I see my expression here, I look that 0 is on the bottom and minus 225 over 2 is on the top. And yet this value is smaller than this value. So I have to write it in the standard form by changing the sign. How do I do this? So I'm going to change the sign. So from minus 0 to minus 225 over 2, e the power u du. To put these limit values in the standard form, I'm going to say minus, this minus comes from here, minus, change the integral, this minus 225 over 2 goes at the bottom. Then 0, which is greater than this one, goes on top. Leave my e function as it is. Now, I'm going actually to integrate a positive function now. So it's going to be plus the integral of e the power u du 0 to minus 22.5 over 2. And now I know how to integrate my e function. The integral of this one is going to be e the power u divided by the derivative of the power, which is 1. So I have e the power u over 1, and evaluate this one as minus 225 over 2 and 0. No c, because this is definite integral. So I can now evaluate this expression using the upper bound, which is 0, and lower bound, which is this one. So then I'm going to have e to the power 0, my u is 0, minus e to the power u, my u is minus 225 over 2. So now my expression is going to be, remember, e to any value to the power 0 is 1, minus e the power 2 minus 5 over 2. This is your function. That's your value. Now, here, there was a mistake here, I think. Let me check here. I'll check it for you before you go here. There's a mistake, actually. The answer should be plus 1 minus that value. Okay? But I think there was a minus here when I changed it. I forgot to put a minus here because between the t here. Here. Up here. Oh, here. Oh, yes, I forgot to put but it was there. I forgot it here. That's why the minus, there should be a minus here. That's why I ended up with this. So the mistake is here. I'll correct it. Okay? Now, this is how you handle substitution method. Now, I just want to go through in the written form, steps we can take. I'm just trying to simplify the situation as much as I can. Now, the steps taken by substitution, the substitution method, I'll just say maybe there's many ways you can do it. I just said the few. I'm just trying to summarize the steps you can take by substitution for you to handle substitution. I just say that if you are faced with a function and the function is a combination of other functions, just see how am I going to handle it. And especially at this module, MAT112P, the only method actually you are faced in this form is substitution method. But I've seen some of you applying integration by parts and whatever. Those are not for this module. But here we just concentrate on substitution method. Now, choose a new variable u, and usually the u is the innermost expression, which I gave you there, the inside function. And after that one, you go, after choosing u, take du with dx. If your function is in terms, if u is in terms of x, then it's du dx with respect to x. Then this one will cancel here, and on the other side, the way we have done the examples. Now, the third step, replace all your terms or all the expression in your original function with all the expressions in, oh, yes. There's a call from Durban, yes?
Hello.
Hello.
Yes, could you please do me one problem?
Okay. Which one?
Okay, can you write it down?
Oh, yes.
It's antiderivative.
The antiderivative or integrate?
The lower bound is 1.
I'm integrating, yeah? Integrate. Is that what you mean, like this?
Yes,
yes. Integrate?
Yes. The lower bound is 1. Upper bound is 4.
Okay.
It is x minus 1.
X minus 1
is over square root of x dx.
Square root of x, eh?
Yes. dx.
Dx. Now here.
Yes. Thank you.
I can separate it. I'll separate this one in two sections. 1 to 4 x to the power square root of x dx minus 1 to 4 1 over square root of x dx. What's so difficult there? Can you see it now? Now here I'm integrating 1 to the power 4, reduce the power there, so I have x to the power half there, dx, minus the integral from 1 to 4, x to the power minus a half, dx. Can you do it now? You can integrate this one now. Power rule. Okay? If you want me to continue, wait. Yeah, because I've separated the two functions. This one over this, I have this one. This one over this, I have this one here with the minus sign. Now here, I'm reducing the exponents because this is the same thing as this one here. Is what I have here is x to the power 1 over x to the power half. Oh, sorry. So here, I have x to the power 1 over x to the power half, which is the same thing, power exponentials you did in high school. So it's 1 minus a half. I end up with x to the power a half. That's why I'm integrating x to the power half from here. I'm reducing the powers. So here also, I'm putting this is x to the power half at the bottom. And then if I put it up above, it will be x to the power minus a half. Then I'm using the power rules to integrate this one. So it's going to be x to the power a half plus 1 over a half plus 1 plus c1. This is a definite integral, so there's no c. Evaluate from 1 to 4. The second one will be minus x to the power minus a half plus 1 over minus a half plus 1. Integrate from 1 to 4. So you have two expressions. There's no constant here because there's a definite integral. Okay? Now, let's go back to our expressions. Daban, I hope this has answered your question and you'll be able to do it. So the simplest way is simplify the function and then integrate each separate functions. Now here, if I go back the methods now, I'm going to show you our steps of integration by substitution. I said choose your u, and usually u is the innermost expression or the inner part, and then take the derivative of u with respect to x or with respect to any variable which you have. After that, replace all your u or all your original expressions in the new variable now. In this case, it will be u. Okay, but I'm not saying u. You can use any other variable. You can use s, you can use t, whatever. But here we are using u, and so on. So all the variables you had, like x or t, you can replace them with a new variable now, which is u, and replace dx with du. Now evaluate the resulting u integral. Remember now the new integral will be in terms of u, which is but step 4 there. And if it works out, then continue. Sometimes the u you choose might not work. Then you'll be forced to choose another u again. Okay? So here that's why I'm saying that evaluate the resulting u integral or the expression which you have got. You might need to try a different u if the first one doesn't work. So it can be try and error method here. Now the fifth part, after integrating, replace all the current u into the new expression you have got into the outcome with the original expression x, which I think I did here. I think I gave it to you. I said that you go back, integrate. After integrating, you go back and replace your variables with u, which the example I did at the beginning here. I said that I picked my u is equal to x cubed plus 5. I differentiated u with, I have this expression. I chose u to be equal to x cubed plus 5. Take the derivative of u with respect to x. I got my everything in terms of u. Go back and replace your wherever there is x with the u. Cancel whatever you have to cancel. I have a new integrand in terms of u with respect to u. I take the integral. Here I come. I have my integral now in terms of the new variable, which is u. I can leave it like this, or in most cases, most people, they want you to go back into the original expression. This is step 5 I'm talking about, that after integrating your integral in terms of the new variable, which is u, you go back and substitute your new variable with the old variable you have, which is x. Okay, that's what I'm talking about in the last step 5 there. Now, these are the examples maybe you can do. I don't think we have time to do all this, but I can do one. This I've done, it's like examples we have done. Maybe I can do, maybe this one here, I can do D. Let me do one, D. Now, here, D is given as integral of tan inverse of x, all to the power, remember the whole tan inverse is the power 2, all over 1 plus x squared dx. Now, when you look at this expression, I'm doing D. You can try A, B, and C, but I'm with U substitution. Maybe I'll tell you on what to substitute. Now, when I look at my D, the expression looks so complicated. And most of you kind of leave it, and yet you can actually handle it if you can take a deep breath and think of your U substitution. Now here, I'm going to take my U to be tan, because if I take this one, it won't help me. So I'm going to ask myself, what did I differentiate? What is the relationship? So when I see this one here and this, I say, oh, if I take the derivative of this one here is here. So if I let my U equal to this, and if I differentiate it, this part might go. So that's why I'm saying let U equal to tan inverse of x. So that du dx is equal to 1 over 1 plus x squared. Remember when we dealt with the integral of arctan, arcsec, or sectan, arctan, arcsec, arcsine, arccos, and all those. So this is the derivative of arctan. Now, make dx the subject of the formula. Dx is equal to 1 plus x squared du. Go back and replace your integral here. My tan inverse is my u, and it is squared, u squared, over this expression here. Maybe it might go or it might not go. And my dx is 1 plus x squared du. So this cancels with this one here. So I want to use the same line. And then here is going to come this one here. I'm going to integrate now u squared du. Now I have the power rule. So this is going to be u cubed over 3 plus c. Now I know my u is arctan, so I'm going to have my outcome is going to be 1 over 3 tan inverse of x all to the power 3 plus c. This is how you handle u substitution. You see now you become so complicated. It looks so complicated from the beginning. Now when you apply your u substitution properly, you end up with a simple integral in the power form. Then you integrate and then go back and substitute your original variable. That's the last step, the 5th step. Now let me go back on the screen. A, I'm not going to do it. You can do it yourself. Try it. A, remember I have x times cos x squared dx. The integral of this one, I'm going to say let u equal to x squared. You can write this one actually and go and do it. Let u equal to x squared. And then when you go and take the derivative, go and simplify, you're going to end up maybe cos u. Okay? Cos u du and so on. Maybe you can go and see. But let u equal to x squared in the part A. In part B, let u equal to 3 sine x plus 4. And then you're going to end up with the integral of u to the power 5 cos x. Now, find dx. Replace dx from du. Remember your du is from 3. Du is going to come from 3 sine x plus 4. And then take the derivative of u, go back and substitute your u and your dx and see the expression you get. In this expression here, you're going to take u equals to x cubed plus 5. Now, if you take the derivative of x of u, you're going to have 3x squared, and go and make this dx the subject of the formula, replace your u, and then and go and replace your dx. The dx here in terms of du, it might cancel with that one, and then integrate. So these are the things you have to do. Take in the first part A, u equal to x squared. In B, u equals 3 sine x plus 4. And in C, u equals x cubed plus 5. Take those and then do it as a homework. Now, I want to go on the part which I wanted to cover, but not this one here. This one is like, you know it. This is like integrating using it in definite integrals. Now, fundamental theorem of calculus. There are two parts of fundamental theorem of calculus. In your book, it says part 1 and part 2. So in other books, this one is called part 1, part 2, and another one is called part 1. But in your book of Smith and Minton, part 1 is this one. Now, they said the fundamental theorem of calculus, part 1. If a function f is continuous on a given interval a, b, and a function, a capital F here, f of x, is any antiderivative of a small function f here, of f of x, then the integral from this a and b, remember a is the lower bound, b is the upper bound, of a small function f with respect to x is equal to an antiderivative. Remember, the big F is the antiderivative. Now, you evaluate that antiderivative at the upper bound minus evaluate the antiderivative at the lower bound. This is the definite integral which I've been doing so far. So this is definite integral or area under the curve. So the definite integral and area under the curve are almost the same thing. Okay? Or use the definite integral to find the area under the curve. Now, the example is this one here. I'm not going to waste a lot of time because we have done it already. So you're integrating this one from a to b, and I have a polynomial here. So integrate this polynomial on its own, this function on part is on its own. You get x cubed over 3 minus 2x to the power 2 over 2. 2 cancels. I have x squared. Evaluate it from 0 to 2. 2 is the upper bound, which is your b, and 0 is your a, the lower bound. Now, I put 2 first. You always put the upper bound first right through. F of b. So f of b is this one here. So this one is my big F. This is my small f. I'm integrating a small f, get my antiderivative, which is a big F, evaluate big F at b, which is this one here, minus evaluate big F at a, which is this one here. So Pete, always after integrating, getting your antiderivative, evaluate the antiderivative using the upper bound first, right through. So put, wherever there is x here, put 2, I get 8 over 3, minus 2 squared, which is 4, in bracket, minus, in bracket, big bracket, put 0, the lower bound now, wherever there is x, which is 0 cubed over 3, minus 0 squared, which is 0. So you have 0 here. So if I simplify this expression, it's going to be this, minus 0, I end up with minus 4 over 3. So this is almost like area under the curve, or definite integral. That's fundamental theorem of calculus part 1. The same thing here, I'm not going to do it, the same thing here. I'm rewriting this expression, this term, with the power. I'm removing the radical sign. I'm using the power here. Integrate, get the antiderivative is here. Your b is there, your a is there. Do the same thing, and you end up with that one. Now, in this case here, I want to elaborate this one here. The same thing which we did. We are saying that I'm going to do this one here. The integral of from 0 to 4 e the power minus 2x dx. Now here, I'm going to remember the e function. We talked of the e function. You leave the e function as it is. I'm going to find, this is my small f. I need the antiderivative. My antiderivative is a big F, which is e with its power. Leave the e function with its power, divided by the derivative of the power, which is minus 2. Remember, when we are differentiating, you leave the e function as it is, times the derivative of the power. But when we are integrating, you leave the e function with its power, divided by the derivative of the power. Okay? So we leave the e with the to the power of 2 minus 2x, times the derivative, the derivative of the 2 minus 2x is minus 2, divide that. And it is definite integral. Then I'm going to evaluate this from 0 to 4. And this is the same thing as f b minus f at a, definite integral. Okay? And now, this is the same thing. I'm going to put my f here. I can put it here. My f, my antiderivative is this one here. Put my b, which is going to be e to the power minus 2, the power 4, 4, over minus 2, minus f of a is going to be e, the power minus 2, times 0, all over minus 2. Now, if I simplify here, I'm going to have minus 1 over 2 e to the power minus 8, isn't it? Plus, minus and minus here becomes plus 1 over 2 e the power minus, to the power 0. So here, because minus 2 to the power times 0 is 0. So here my answer will be minus 1 over 2 e the power minus 8 plus 1 over 2 times 1. So I can say a half minus 1 over 2 e the power 8, if you want to simplify. This is how, I just want to do it because I wanted to highlight the e function and how to use the substitution. So this is definite integral. And here, what I'm saying here, note what I'm writing, what I'm talking about, I've put it in words. I say that note that in the example C here, the integral, which is e function, you leave the e function, okay, of the e function, just the e function with its power divided by the derivative of the power. That's so. That's how you integrate the e function, okay? Plus a constant if it is a definite integral. But if it's a definite integral like this one, no constant. Now, the same thing here. Remember, this is an example where n power is minus 1. Now, here, the last one is going to be minus 3 to the minus 1, 2 over x dx. And now here, my lower bound is minus 3, my upper bound is minus 1. Minus 1 is bigger than minus 3. It's in the standard form. It's okay. So this one, I can rewrite it as 2 integral of minus 3 to minus 1, 1 over x dx. Remember, I cannot use the power formula because n is minus 1. And since it's minus 1, there's a special formula which we have, or which we saw. It is 2 ln of x, and evaluate this one from minus 3 to minus 1. And remember, there's an absolute value there, no constant. So when we go through, we are going to have 2. Actually, there's a mistake here, I think. 2. So ln of minus 1, okay, it's undefined, minus, which we can't, absolute value, remember? That's why we remember we are taking absolute value, minus 2 ln of minus 3. Remember, when we say you must put absolute value. So here our answer is going to be 2 ln of 1 minus 2 ln of 3. So here this is, ln of 1 is 0. So I'm going to have 0 minus 2 ln of 3. That's how the answer is. Now here there's a mistake here, sorry. So just leave it 2, leave 9 out, and just it's 2. It's 2 here, okay? And this is ln, not in. Ln, L-O-N. It's not I, it is L-O-N, okay? And that's natural log of 1 is 0, times 2 is 0, then 2 times ln of 3, and it becomes negative. So I end up having my answer is minus 2 ln of 3. Now, the next one is the fundamental theorem of calculus, and here, finding the area. Now here, remember I told you on top that definite integral is the same thing as area under the curve. So you can see this example. They say that compute the following integrals using the fundamental theorem of calculus. Or maybe what I can say, if f of x is equal to sine x, and sine x is greater or equal to 0, that means above the x-axis, find the area under the curve on this interval 0, 0 pi. Now here, that's the question that they're asking you. Find the integral of that, or find the antiderivative of sine x. Now here, the same question is that, what is, if I have f of x is equal to sine x? And they said sine x is above x-axis, is greater or equal to 0. So in the graph, if you can remember your graphs, y here, x there, the sine is this one here. Okay, so this is 0, this is pi, and this is here is going to be pi over 2. Now, they're saying above the x-axis, so that's the only function we have. This one here, they said y, or y is equal to sine x. And this part here is x-axis, which is the same thing as y is equal to 0. Now, they're asking you to find the area between that curve. Now, how do we handle this one? Remember, we are going to have area is the same as integral, the flat integral from 0, because I'm saying from 0 to pi, of the function, the top function, remember when you're finding areas, is sine x minus the bottom function here, which is x-axis, which is 0, y is equal to 0, which is 0, dx. That's how we are writing this expression. Now, to simplify it, I'm going to integrate 0 to pi of sine x, because sine x minus 0 is just sine x with respect to x. Now, the integral of this one, you ask yourself, what is the antiderivative of sine x? You ask yourself, what did I differentiate to get sine x? So actually the integral or the derivative, the antiderivative of sine x is equal to minus cos x. I differentiated minus cos x to get sine x. That's why the antiderivative of sine x is minus cos x. And it's definite integral because it's from 0 to pi. Now I'm going to evaluate my value, which is actually end up with a real value, which is an area. So this one I'm going to put my pi first, the top upper bound. So it's going to be minus from the formula cos pi minus from the formula minus cos 0. So it is upper bound minus the lower bound. So here I'm going to have minus and from the formula the cos of pi is minus 1 minus this one here and the minus here, cos 0 is 1. So I'm going to have plus 1 and the answer is 2. That means that the area under this curve between x0 and pi is equal to, area is equal to 2 square units. Okay, square units. That's how you find the area. So area and definite integral are related. That's how I was trying to do it. I've done it for you. This one I've done. Now, the thing I want to touch quickly is fundamental theorem of calculus part 2. Actually, this is the crucial part I would like to handle. Fundamental theorem of calculus part 2. This is where you have fundamental theorem of calculus part 2. Now, this fundamental theorem of calculus, you are given a function, and the function, remember, it looks like a definite integral. You look at it as if it has a lower bound and the upper bound. But now when you are faced with this integral, if these are real numbers, if the lower bound is a real number like 4 and the upper bound is a real number like 5 or 6, then we are talking of definite integral. And that is the fundamental theorem of calculus part 1, which we have seen already. But when we look at this, we are seeing that 1 is a constant, the lower bound is a constant, the upper bound is a variable. And I have an antiderivative here. I have a function which is a capital F here, and I have a function which is a small f. Remember, this capital F is with a f of x, and the small f is with t, and I'm integrating with respect to t. Now, when I see expression like this, I think of fundamental theorem of calculus part 2. Okay? And how does this work? In other words, that if I have a function, f of x, f is a capital F, is equal to the integral from a to x. A is a constant and x is a variable. F of t with dt. Here, I'm asked to find the derivative. If you find the derivative of this, these are questions actually will be asked for you to find the derivative of this form, not to integrate, to find the derivative, because you have already have the integral, so you ask you to find the derivative of this. So they're asking that this is the antiderivative of this. And if I differentiate this, what do I get? Okay? So these are the kind of questions where you have to find the derivative of the left-hand side. Now the derivative of this one is, which is d with respect to x, d, dx of this function, is the same thing as the derivative with respect to t, because of this, the right-hand side. The right-hand side here. So here I'm taking with respect to x on the left, I'm taking the respect to d, to t on the right, because this should cancel with this one here. Now, this, I'm going to have f prime or df over dx, which is written as f prime. And if I differentiate the integral, I remain with the function itself, which is f of x, and replace this t with that x there, times the derivative of x. Now here, that's why we always have f prime of x is equal to f of x times 1. And we see that therefore, we have f prime is equal to f of x. What in words? We'll leave the function as it is, take the derivative of the left, the right, leave the function as it is, f of t, replace that t with the x there, times the derivative of that x there. This is fundamental theorem of calculus part 2. Another example, if I extend on this one here, let me start with this one here. No, this you can do. This one you can do. I'm here now. The fundamental theorem of calculus. Let me do this one also. Now here you have the integral of from 1 to x, 12t to the power 5 dt. And this is called f of x is equal to that one. Now to apply the fundamental theorem of calculus, so this means that f prime on my left hand side is equal to, leave the function as it is, which is 12. Replace t by this variable here, which is x. And this t is the power 5, so that means x is the power 5, times the derivative of this one here, not here, but here, which is 1. So that's why I'm going to have f prime of x is equal to 12x the power 5. No constant. When you are dealing with the fundamental theorem of calculus part 2, you don't put on a constant. So another example, which is more complicated maybe, is this one here. This is where I want you to pay attention, even if you don't write anything. Now you have, if f of x is given as the integral of 2x up to the x squared, square root of t squared plus 1 dt. Now the question is compute f prime of x, or find f prime of x. How do I handle this one? First of all, I see that my upper bound and my lower bound are variables. For the fundamental theorem of calculus part 2 to hold, the lower bound must be a constant and the upper bound must be a variable. Now I see here lower bound is a constant, is a variable, and the upper bound is a variable. So before I go on with the fundamental theorem of calculus part 2, I'm going to split this bound. I must create a constant in between these bounds, okay, between this lower bound and the upper bound, so that I can be able to apply fundamental theorem of calculus part 2. What do I do with this one here? So my function becomes, I write my function f of x as integral 2x up to a constant. This constant must be between x, 2x and x squared of this function t squared plus 1 with the root of it dt, plus, I'm dividing the function in two sections, plus the integral from the constant here up to the variable x squared with the same function with dt. So I'm dividing my integral in two parts so that I create the integral with a constant, so I can be able to apply fundamental theorem of calculus part 2. Now I have a variable to a constant of this function with respect to t, and I have the integral, a constant to a variable of this function with respect to t. Now here I cannot apply fundamental theorem of calculus immediately. I have to put it in the standard form, because to apply fundamental theorem of calculus part 2, the lower bound must be a constant and the upper bound must be a variable. Now how do I do this on this part? This part is okay. The second part is okay. I'm from a constant to x squared. But here I have 2x to the power, the upper boundary is a constant. So I have to put it in the standard form like here. So I'm going to create a minus sign. The minus will change the bounds from the bottom to the top or from the top to the bottom. So I'm creating a minus, the integral. Now the c comes at the bottom. The 2x goes at the top. Then my function stays the same, dt, plus, this is in the standard form already. I'm leaving it like that. C x squared t squared plus 1 all the power dt. Okay, now I'm going to apply my fundamental theorem of calculus part 2 on this one here. Okay, remember, we leave the function as it is, replace t by that variable, time divided by the derivative, time the derivative of the power. Fundamental theorem of calculus. Now we are integrating. When we were integrating before, we are saying divide by the derivative of the power. But now with fundamental theorem of calculus, we multiply through by the derivative of the power of the variable. Now, how do we do it? We are going to say my function now was t squared, square root of t squared plus 1. So I'm going to replace t squared by 2x minus 2x all squared plus 1 square root of that times the derivative of 2x with respect to x. Okay, that's the first one. The second one, plus the leave the t function as it is, which is replace t by 2x, x squared, sorry, x squared, x squared, all t squared plus t square root of that times the derivative of the x power, which is x squared. Now my answer here is going to be minus the derivative of 2x here is 2 times the square root of 4x squared plus 1 plus the derivative of x squared is 2x times this squared is x to the power 4 plus 1. That was your answer. Okay, I go back. I'm going to repeat the explanation. The fundamental theorem of calculus part 2. I'm given expression. You're integrating from a variable to a variable. But the fundamental theorem says that if you have to integrate from a constant to a variable, then I leave the function as it is, replace that variable by the power, by that variable, replace this variable here by this variable times the derivative of this variable. But now in this case, both lower bound and upper bound, both are variables. I cannot apply the fundamental theorem of calculus part 2 directly. I have to split these bounds in two by creating a constant c. This constant must be between these two bounds, this x2x and x squared. And I have done it like this, leave my expression, separate the two. I'm putting this one in the standard form by creating a minus sign because I want a constant to be at the bottom and a variable on top. I'm doing it here, and I've done it. This one is already in the standard form. The constant is at the bottom, the variable is on top. I'm leaving it. Then I'm applying my fundamental theorem of calculus part 2 on these expressions. Now, here I have replace t squared by 2x all squared plus a constant. This one is not affected. With the minus comes from the other side. Times the derivative of the variable, which is 2, the derivative of 2x, which is 2. You get it here with a minus here. This one here, replace t by x squared, because that's what the second here I have x squared. Replace t here by x squared. So it's going to be x squared all squared. So I'm going to have x squared all squared plus 1. And I have x to the power 4 plus 1 times the derivative of x squared, which is 2x. That is my answer. No C. No C.
Hello.
Is that a call from Durban?
Yes.
Yeah, can I help you?
Yes, please. From the problem that we are just doing.
Yes.
Yes, I want to know, as soon as you replace t's with 2x, so you remove the integral.
Yes, yes. You remove the integral. Okay, and leave the expression itself, and multiply through by the derivative of that variable.
Okay, so you don't find the antiderivatives. You just replace them and then remove the integral.
Exactly. Just remove the integral sign.
Thank you.
Just remove the integral sign and replace your t with a variable.
Okay.
And you don't put a c.
Okay.
Thank you.
you.
You're welcome. I want to run through with areas under the curve. But the main thing actually here, areas under the curve is definite integral, which I've done already. So the only thing, I'm not going to do it actually, I'm just going to explain here. You just have to know which function is on top, which function is at the bottom, and then plug in your function. So the area bounded by curves with the limit values or the boundaries. So if you're finding the area between A and B, and you have a function f is on top, and the function g is at the bottom, so it's always the area is equal to the integral from the lower bound A, up the upper, which is A here on the left, up to the upper bound B, which is on the right here. The top function, f of x, which is above, minus the bottom function, which is g of x, which is below. Okay, that's what you have to remember. And usually, I encourage the student to draw the graphs briefly so that they can know which function is on top, which function is at the bottom. Now, let's run through examples quickly. These one are substitution, whatever, no. May I run through that one? Here, I just wanted to go through the substitution method here because that's what we're going to deal with. Just run through, I've just gave you this example. I want just to run through it. Substitution method, I'm letting u equal to x to the power 5, then du and so on, and then change your limits and so on, then find the value. So this is, I'm just reminding you that a definite integral, I'm using this, a definite integral by substitution method is the same as the area under the curve. So that's why I gave this example first. But let's go back, let's go to our area under the curves. Now, the question would be, find the area under the curve bounded by the y is equal to 3 minus x and y is equal to x squared minus 9. Now, if you can take time and draw the graph briefly so that you can know which graph is on top, which graph is at the bottom. So usually most of you just guess. And then if you're lucky, you can guess right, but sometimes you can guess wrong, okay? So here I'm saying that area under the region determined by intersection of two curves, limits of integration x are the x coordinates of the points of intersection if you are not given the points of intersection, okay? Now to find the limits, equate the two functions and find where the two functions are crossing each other. But if they have given you the limits, where the points of intersection, then you don't have to do all this. But if the points of intersection are not given, then you're going to equate two graphs, solve them simultaneously, solve them and find the points of intersection. So here, the points of intersections were not given. I'm just given two curves. The points of intersection were not given. I equated the two equations, find the points of intersection by equating the two equations, solve it. I'm getting the point of intersection is x is equal to 3 and x is equal to 4. That means that the two graphs are cutting at x is equal to minus 4 and x is equal to 3. Now to get the y value, which if you need it, but you don't need it actually. So I just need my points of intersection. I need my a, which is minus 4, and I need my b, which is 3. Now, to find my area of this graph function, this graph, I know that my linear function is at above, my parabola is below. So in my formula, I'm going to say I'm integrating from a to b. My a is 4 minus 4, my b is 3. I got them by equating the two equations and solve them. Now, it's my upper function, which is the linear function, minus the lower function. And you can see that from a is equal to minus 4 to b is equal to 3, the whole function, the whole polynomial, the whole parabola is at the bottom. And in the whole interval, the line is at the top. So I'm going to say integrate from minus 4 to 3, the top function, which is a linear, minus the bottom function, which is a quadratic. And remove the bracket, have this expression and simplify. So the expression is this one. So now I'm going to integrate this one, a term after term, term by term. This one here will give me minus x cubed over 3. This one here will give me minus x squared over 2. This will give me 12x. Evaluate from minus 4 to 3. So you are going to put in 3. That's it. This is my antiderivative, big F. This is my antiderivative. Evaluate big F at 3 minus evaluation of f at minus 4. So put in 3 right through into your integrand with your antiderivative, minus from the formula, minus f of a. My f of a is all this. If you simplify, you get this answer, and that answer is the area under this curve, which is bounded here. The second example is the same thing. Now here, they are saying find the area bounded by y is equal to x squared, and y is equal to 2 minus x squared. So actually, you can just draw the graphs quickly if you can. I'm sorry, here there's a mistake here. There should be a line here because I'm given bounds here between 0 and 2. I'm going to find the area between x is equal to 0, which is the y-axis, and x is equal to 2, which is, actually here, I'll draw it here. So the area will be, here, if I can draw it here, roughly, it will be this one here. Sorry. Oh, okay. Okay, so the area, the area I want to show you, so it's going to be this one and something like this one. And the area they want, here up to 2 here, which was left out. This line was left out because they said between 0 and 2. This is y, this is x. Now here, this is my area of y is equal to 2 minus x squared. And this area is y is equal to x squared. And this is the line between 0 and that the area I want is all this area, I think. So bounded by this and this one, I think. Okay, because they said between this one here. Anyway, let me use my solution. Actually, I don't have much time. Now here, you're going to draw your sketch. I think put your line here, which you are missing out there. Get the area. Now it's going to be this area, this graph minus that graph, integrate from 0 to 1, because they are cutting at 1, plus this area, this graph, minus this area is not there because x-axis is not included. Okay, so this area, that graph minus this graph, integrate from 0 to 1, plus this area, which I have here, from 1 to 2, that vertical line. So this will be graph x squared minus this bottom. So it will be blue here minus red here, while in this section, it will be red minus blue. And that's what I've done. So the area is from 0 to 1. The top function is the parabola facing down minus the parabola facing up, 2 minus x squared dx, plus the second area is the parabola, the x squared, which is above, on top in that interval, minus the parabola at the bottom, which is x squared minus bracket 2 minus x squared, integrate from 1 to 2. So now, integrate each function separately, simplify, integrate. After integrating, evaluate the first integral from 1 to 0, put 1 first, minus, put 0 again. This one here, put 2 first, minus, put 1 again. When you simplify all this, what I'm doing, the answer will be 4. So this means that this is the area you obtain by evaluating this area plus the area here. I don't have much time. Now, this example I want you to see also. Always, we don't integrate with respect to x only, or we don't take the bounds only being by x. Usually, we see how the function is sitting or how our graphs are sitting. Like in this example, they say find the area bounded by the graph x is equal to y squared and x is equal to 2 minus y squared. If we draw our graphs, we see this expression, this graph here. Now, it will be easier to say the right function minus the left function. And the right function is in terms of y, and the left function also is in terms of y. So now our expressions are in terms of y, so our bounds, our limits values would be the y values, not x values. So we are going to integrate with respect to y. So it's going to be the right function, which is this one here, minus the left function, which is this one here. But from minus 1, y is equal to 1 minus 1 to y is equal to 1. So that will be our bound with respect to y. So we go and integrate, simplify, find the integrand, find the antiderivative, integrate this expression with respect to y, and then we end up with this. This is our antiderivative or our integrand. Evaluate from minus 1 to y, these to 1. These are y values, the limit values. So you do the same thing, you find the area is equal to 8/3. You can also integrate this area with respect to x, but you're going to cut the function in two parts. You're going to integrate from 0 to 1, then it's going to be this, whatever, minus this one. You can see that it's going to be a lot of work to do. You can also do it with respect to x, but you're going to integrate this function cut it in two. You're going to say that this part of the parabola, the positive part, minus this parabola itself, the negative part, integrate from 0 to 1, plus integrate the positive part of this parabola minus the negative part of this parabola, integrate from integrate from 1 to 2. These limits will be x values. But you see that it's a lot of work. Now here, I didn't do first differential equations. I couldn't do first order differential equations. Maybe you can go through them and do them yourself. If you have problems, you can call me, and you have my contacts on the in the tutorial letters. But I just wanted to write through. Differential equations is actually the derivative is a function where you have equation in terms of y dy. And we're dealing with you here in this math 112p. You just have to deal with separable differential equations. And separable differential equation, you always group y's with dy, group x's with dx, and integrate. And after integrating, you're going to have a constant, and then solve for y. But if you have initial value problems, these initial value problems will give you a constant of integration. You will find the value of a constant. So unfortunately, I don't have much time to do this question. You call me if you have a problem. All these examples I have done for you. And in decay, growth and decay. You have a lot of examples here. You can go through in even your study guide. Unfortunately, I don't have time. This is all the time I have to cover the material of today. Unfortunately, I didn't finish the differential equations, and growth and decay. But if you have any problem, please call me and I will help you through the phone. Thank you very much for listening, and good luck in your exam. Bye-bye.